Welcome to the section webinar of the Emerging Applications section. Today we will have Anna Calissano presenting. Anna Calissano of University College London, who works also in an honorary role at the Imperial College in London. Her presentation is in, I would dare to say, an emerging area in mathematical statistics, broadly defined, geometric statistics. Let Anna correct me if I'm wrong. And the title you see already on the slide: statistical analysis of sets of graphs, from labeled graphs to spatial graphs. Anna will have about 40-minute presentation. The meeting will be recorded. It will be later accessible online, like you already have in the chat. Please insert your questions in the chat. Some might be already asked shortly during the presentation, and if not, in the follow-up debate. Anna, please, the floor is yours. Thanks.
Thank you, Andrea. Thank you for having me here today. So I'll present an overview on how we can do statistics when you have a set of graphs. And I'll talk about two specific types of graphs, what we called unlabeled graph and spatial graphs. So it's a bit of an overview talk. Okay. So let's start by introducing set of graphs. So what do we mean by set of graphs? I like this definition of object-oriented data analysis perspective that was introduced by Wang and Marron. That divides the analysis of data like graphs into two different approaches. The first called the so-called first generation approach and the second generation approach. By first generation approach, we mean the analysis of one single network datum, so one single graph, with a set of nodes, a set of edges, and an attribute function. All the standard network analysis, let's say, falls into this category, where the questions might be how can we classify the different nodes, how we can predict one edge into the graph, and so on and so forth. So the graph is usually an attributed graph and can represent, for example, a public transport network, like the one in the picture. This is what is called the first generation approach. The second generation approach is when we move from one single object to a set of objects, in our case, a set of graphs. So each observation is now a graph with a set of nodes, a set of edges, and an attribute function. When we have a set of graphs in the second generation approach, the questions are different and regards, for example, how can we predict a new graph, or how can we classify this graph? How can we study the distribution of this set of graphs? So this is what we mean by a second generation approach when we talk about a second generation approach to a set of graphs. In this example, we have a set of graphs that are different public transport systems in different cities, just to give you an example. Now, what are unlabeled graphs? Unlabeled graphs are graphs where we have uncertainty around the node labels. This is a very simple example. So suppose we have two graphs that describes the social interaction between different subjects. For example, Matilde, Lorenza, and Vittoria. If I have Matilde, Lorenza, and Vittoria as my nodes in my different graphs, so in the first and in the second graph, these type of graphs are called node labeled, or simply labeled graphs, because we know which node corresponds to which other nodes in the two graphs. So I can compare these two graphs directly. Another type of graphs, which are more interesting to study in terms of theory, like they are a bit more complex, let's say, are what we call node unlabeled graphs, or simply unlabeled graphs. So this type of graphs are nodes where we have uncertainty around the node labels. So, for example, you have these two graphs and you don't know which nodes correspond to this first node in the second graph. So we need to handle this uncertainty somehow. So today I would like to talk about two different types of uncertainty, let's say, around node labels. The first we call the abstract graph, the second we call spatial graphs. And these are two completely different, let's say, type of graphs that share the same problem of uncertainty around the node labels in the different graphs. So by abstract graph, we mean graphs that doesn't have additional specific attributes on the nodes that you want to take into account. So this is just a motivational example. Suppose you have two teams, two football teams that plays one against the other, and you study what is called the player passing network. So you have for each team the number of passages between players within the team. So you have two teams. In this example, you have Croatia and France, and you want to be able to compare the player passing network of these two different teams. To do that, you need to somehow match the players across your teams. And the uncertainty is around the node label, so the player's name, and you want to consider this graph and compare this graph as purely unlabeled. So this is what we call abstract graph, because we are interested only in the graph structure, despite the name of the player involved in the network. The second type of graphs that I want to talk about today are what we call spatial graphs. These are completely different, but they share some common problems with the abstract graph. Spatial graphs comes from the skeletonization of geometrical objects. So this is an example of a specific tissue, which is a cardiac tissue. Where you have a fibrotic tissue in black and what is here in white is a muscle, so what is called an healthy tissue in this example. And we are interested in studying this structure, the black structure. So we can extract this object and simplify this object using a skeletonization procedure. If we do that, we obtain what is called the skeleton graph. That is a spatial graph because our node has a spatial position in R2 in this case. So if I want to compare a set of spatial graph, I have again uncertainty around the node labels because the label that you see here, like 1, 2, 3, 4, 5, 6, doesn't really make sense. So I don't want to compare one with one just because I labeled this node as 1. So I again want to get rid of this label information, but the matching, the alignment between this graph is different from the one I need for the abstract graph. So today what I would like to do is to describe how you can handle uncertainty around node labels in these two types of graphs. So to summarize, unlabeled graphs require a concept of matching or alignment, and this concept needs to be tailored according to the type of application and the type of graph you're working with. So I'm going to talk about abstract graphs first. I will describe a geometrical embedding for this type of graph, and I'll talk about how you can do statistical modeling, in particular regression, when you have a set of abstract graphs. And then I'll move to a second type of graph, which are spatial graphs. I'll describe a different geometrical embedding for this specific type of graphs. And then I'll describe quickly how you can do, for example, testing when you have a population of spatial graphs. So this is what I would like to do today. I know it's ambitious, but let's hope you will get something out of it. So let's start with unlabeled abstract graphs. So this is a motivational example that I have already explained. So it's just to give you an idea of what I'm talking about. So we have to think of abstract graphs as a graph in which I don't want to keep track of the node labels, and I want to compare this graph despite their node labels. So for example, I have the player passing network of different teams during a specific tournament. These data are, for example, open data from FIFA 2018. So I have a population of graphs. Each graph represents a player passing network of a given team during a given match. It's just a motivational example. So how can I study this object in more general terms? I'll focus on directed and undirected graphs. So the theory covers both types of graphs. We have a finite number of nodes, and we have Euclidean attributes on the nodes or the edges and the edges of my graphs. So for example, I have this graph that can be represented as an adjacency matrix, a 3 by 3 adjacency matrix, which is a standard representation for graphs. Now, the point is, how can I handle uncertainty around the node labels? The idea is to use a permutation action. So this graph can be turned into these other two graphs by permuting the node labels. And this is obtained by, one way is to apply a permutation action that here I'm calling T, to the rows and the columns of my adjacency matrix. So I have a permutation acting by conjugation to the set of adjacency matrices. By doing that, I can define what is called the graph space. And graph space is defined as a quotient space, Gn, x over T, obtained by applying the permutation action T by conjugation to the space of adjacency matrices. So the adjacency matrices are represented as a point in R n times n, because we have weighted the graph with Euclidean attributes. So I can embed my adjacency matrix in the Euclidean space. Now, the first thing is to define a metric to compare these unlabeled graphs. This metric is basically a quotient metric. So I define a metric dx between adjacency matrices, and this induce a quotient metric between equivalence classes of graph. And this distance that you can see here between the equivalence classes x1 and x2 is defined as the optimal permutation matrix, so the minimum over the set of permutation matrix of my permuted graph x1 and x2 using the metric dx between adjacency matrices. So this is a standard way to define a metric on a quotient space. I can also define something more than just the metric. I can define what they're called generalized geodesics. So these generalized geodesics are extension of straight line planes and hyperplanes from the quotient space, from the total space to the quotient space. So I have x over T, which is my quotient space. I define my delta, which is a generalized geodesics, as the canonical projection of gamma, where gamma is a straight line or a plane, hyperplane, so higher dimensional object in my space of adjacency matrices. Pi is what is called a projection function or canonical projection that takes a point in X and return its equivalence class. So this is another standard way of defining geodesics in a quotient space. You can notice that I'm not using any tools from Riemannian geometry here. So I'm just working with a metric and what is called a generalized geodesic. So let's have a visualization that might help understanding what we are doing. So X is the space of adjacency matrix. So I have the set of all my adjacency matrices. The adjacency matrices that are permutation one of the other all collapse into one point when I go to graph space, which is a quotient space. So every point in my graph space is a set of all possible permuted graph, so all possible permuted adjacency matrix, starting from an adjacency matrix X. So it's an equivalence class, what is called an equivalence class. I can define the distance between two equivalence classes by searching for the points that are closer, the representative adjacency matrices, the representative points that are closer to each other with respect to the metric in X. So this, for example, these 2 points, which are aligned. I can also define a geodesic between 2 equivalence classes as the projection of geodesics, which are straight line in this case, between adjacency matrices. So these are the tools that are a visualization of the tools that I just introduced. So we have metric and geodesic. Now, the final goal is to define statistical methodology of different type for data in this quotient space. The first result is that this quotient space is not a manifold. It is actually what is called an orbifold or a stratified space. This is because our action is not free, so I have equivalence classes of different dimensions. So there are quotient spaces that are manifolds. This is not one of them. And this is a bit of a pity because there is a lot of literature that define and extend statistical tools for manifold, for data on manifolds. So we cannot really use take tools from that literature, but the positive on the positive side, on a positive note, the space is a metric space and it is a geodesic metric space. So we also have geodesics. So what we would like to do is to use what we have to extend different statistical methodology. So this is a very, very short summary of the geometrical characterization of this space. So as I said, we can define methods based on the metric and the geodesics. And today I would like to focus on one specific method, which is what we call the generalized geodesic regression model. There are other methods available that we or other co-authors defined in the very same space. So there is the Fréchet mean, for example. There is a generalization of principal component analysis. And we have also tools for uncertainty quantification for graphs. Today, I would like to talk about the regression model, because I think it's the most intuitive, let's say, to understand. And maybe it's also the one I like the most. So let's talk about how we can build a regression model in this quotient space. So the input data are S1, X1, Sk, Xk, where Si is our regressors in Rp, and Xi is our unlabeled graph in the graph space quotient space. So the objective is to define a function f, so a regression model that goes from Rp to our quotient space. And this is the interesting part because there are a lot of methods that use graph as regressors, while what we want to do here is to build a regression model that is able to interpolate between unlabeled graphs. So this is what this f will do. And as all this model, what we would like to do is to minimize the prediction error. So we would like to minimize the sum of the distance between the quotient, the point in the quotient space xi and our prediction. So again, by using this illustration, like what we would like to do is to be able to fit a regression model in the quotient space. What we know is how to fit the model in the total space. So we know how to fit a regression model between adjacency matrices, because this is just an Euclidean space, so we know how to do it. We don't know how to use this model to extend to the quotient space and to potentially fit the regression in the total space by having a result for unlabeled graphs. So this is the missing point, so these two question marks. So what I'm going to do now is first define a model in the quotient space and then defining a way to fit the model between adjacency matrices. So that's the idea. So first thing is to define what we call a family of generalized geodesic regression model. So we are considering what we call f beta. F beta are functions from Rp to the quotient space. And these f beta are defined as the canonical projection of h beta function. These h beta function are what before I called h when I called gamma when I was defining the generalized geodesics in general. Now I'm selecting a specific set of h beta, and these h beta are, as you can imagine, a regression model in between adjacency matrices. So the idea is to consider only the canonical projection of a subset of straight lines, which are the ones that can be parameterized as a regression model. So the regressors and some coefficient beta, as all regression model in the Euclidean space. These f beta define what is called a family of generalized geodesic regression model that goes from Rp to the quotient space X over 3. Now, this answer, let's say the first question mark. So we have now a family of generalized geodesic regression model that are defined as the canonical projection of regression model between adjacency matrices. The question is, how can we basically select optimal candidate in order to be able to fit the regression model between adjacency matrix? So the idea is to use what we call the optimal regression alignment. So the optimal regression alignment is the selection of a specific candidate in the equivalence class that makes sense for the given problem that we have at hand. So if you have an equivalence class xi, and we would like to select an adjacency matrix to fit our regression model, the intuitive idea is to select the permutation that get us closer to the current estimation of our H beta. So this is what we call an optimal regression alignment. So the graph representative Ti xi is in optimal regression position with respect to the regression line f beta if the distance in the total space between this candidate and my regression between adjacency matrix is equal to the distance between the equivalence class and my f beta. So this optimal alignment regression is a tool that we're going to use to fit iteratively a regression model between adjacency matrix. So the idea is the following. So we have a generalized geodesic regression defined in the quotient space. We know how to fit an Euclidean regression in the total space. The idea is to fit a regression model to start with the first fitting of the regression model between adjacency matrix, where we select some random candidates of our equivalence classes, and then do an optimal regression alignment to search if there are other candidates that are closer to the current estimation of the regression model, and then iteratively refit the regression line and realign the point with respect to the prediction along the current estimation of the regression line. So this algorithm allows you to fit a generalized geodesic regression in the quotient space and obtain and converge to a local minima. So basically, we define this algorithm that is called align compute for estimating, for having statistical estimator in the quotient space using the property of the total space, which is the space of adjacency matrices. So this is pretty much the idea behind, and the same strategy has been applied to estimate a fresh mean or principal components. This is the general idea behind all the tools that we developed in this quotient space. So let's see how these methods work in practice. So we have this player passing network example where we have 128 player passing networks of different match and different teams during FIFA 2018. So we have SI, XI. XI is the player passing network of different teams, while SI is the number of goals scored by the team during all the matches. And the idea was to study, given the number of goals, how the player passing network looks like when you increase the number of goals. And what you can see here is the prediction of the specific player passing network given the number of goals. What you can see, and I think it is a nice example, is that you have a much more diffuse, and we can say chaotic player passing network when you have a lower number of goals, while you have a very clear network structure and strategy of player passing network when you score a high number of goals. So these sport data are very rich and can be studied in many different ways. This is just an example to show how you can use this model. And just to keep in mind, we are comparing different teams. So that's the reason why we need to have a model that accounts for unlabeled graphs, so uncertainty on the node label. So getting rid of the actual player name in order to be able to compare the data from the whole set. So to summarize, what I did in this first part of the presentation is to describe one specific data object, which is what we call the abstract graph. I define a possible geometrical embedding for these graphs, which is what we call the discrete quotient space. And I describe the geometry of this discrete quotient space and how we can do statistical modeling, for example, how we can build a regression model for this type of data in this type of embedding. So you can find more detail in these two papers. In the first one, we describe the regression model, and the second one is a more general paper where we describe the embedding and all the geometrical property of this specific graph space. And we describe also how you can do principal computing. Now, the second part of the presentation is about spatial graphs. So I would like to describe how we can study another type of graph, which are spatial graphs. So here the motivation is actually more applied. So the theory that I described before is very general, while here the motivation, I believe the theory is also general, but we have a very strong motivational example. So we have a data set that motivated the development of this theory. This data set is a data set that we have in collaboration with the colleagues in Ghent, and is a data set that contains histopathological images of cardiac fibrotic tissue that has been obtained from from basically 10 ventricles of human hearts of patients that has been under heart transplant or that died and donated their heart. So the raw data are these ones. So we have the left ventricle and we have slices, and these slices contains two material thanks to a contrast liquid. So we just have two materials here. One is the fibrotic tissue that you can see in red, and the yellow is the muscle. I don't know if, yeah, I don't have a slide here, but just to give you a very quick overview, cardiac fibrosis is a pathology that can develop within the heart when the extracellular matrix, so the space between the muscle cells, start to grow, so overdevelop. And this pathology can cause problems in the pumping of the heart, so in the functioning movement of the heart and in the electrophysiological activity of the heart. This pathology is very common, but is not very easy to study with the MRI or CT scan because the images are not very clear, but can be studied using histopathological images, which is what we have here. So the question that they have is, what is the shape of the fibrotic tissue within the ventricle? So to do that, we decided to study what we called isolated cluster or isolated fibrotic tissue, which are all the isolated fibrotic tissue that we have in all the slices. So the original data that we end up having and that we end up working with is a structure like the one you see here, which is an isolated patch, an isolated cluster of fibrotic tissue. What we are doing is to summarize this object with what we call a spatial graph by using standard skeletonization procedures. So we extract the medial axis and we turn this object into the one on the right. This is a spatial graph, a simplified spatial graph that has nodes in R2, and we decided to encode some information on the edges, which represents the dimension of the area under that specific edge. So for example, this edge has a bigger area than the one here on top. So we encode the percentage of area under each edge as an attribute on the edge. So spatial graphs are defined as a triplet, x times a, the x and mu, where x is the set of nodes, the X is the connectivity structure. So in our case, we define the X as the shortest path between each nodes that is weighted with the percentage of area. So it's a weighted shortest path. A is the set of coordinates in R2 of all our nodes in the graph. And mu is a measure that we put on the nodes of our spatial graph. And this measure is gonna be useful when we compare to spatial graphs. So this is our definition of a spatial graph that we are gonna use to summarize the structure of this cardiac fibrotic tissue. So we have now a set of spatial graphs. And as you can imagine, the variability in the structure of these objects is very, very high. So we need to find a way to compare these graphs, accounting for the different number of nodes, the different size, their rotation, and all the possible group action that can appear when you compare these type of objects. The idea is to use what is called a fused Gromov-Wasserstein distance. So we are adapting this distance introduced by Titouan Vaillet and Rémi Flammary in 2020, and we are going to adapt it to our context. This distance is called fused Gromov-Wasserstein because it combines two components. So the first component is a distance between the spatial coordinates of your nodes, while the second part is the distance between the connectivity of the graphs. These two components are weighted by an alpha, so you can balance these two components using this alpha parameter. And this distance is obtained, the distance is obtained by searching for what is called an optimal coupling, that here is called Pij pKl. This pi is basically assigning a coupling between the set of nodes of one graph and the set of nodes of the other graph. This distance is, let's say, a good flexible idea to compare spatial graphs because it accounts for both the spatial and the structural component. This is like a summary visualization. So, for example, if you are comparing these two structures, which are extremely different, what you're doing is accounting for the spatial distance between the node position and the distance between the connectivity that is encoded in the second part of the metric. And if we look at the coupling, here the nodes are colored according to the actual optimal coupling that was found when we ran the algorithm for computing the metric. This is, we are coupling this node with this set of nodes and this node with this other set of nodes. So these metrics are a good choice because allow you to compare graphs with a very different structure and different number of nodes. So that we found that they were the optimal choice, let's say, for comparing this type of graphs. Now, we would like to make our metric invariant with respect to rotation. Why? Because if you look at the slice, this is our original data. The fibrotic tissue grows following a certain direction, which is the direction of the muscle fibers of the heart. So there is clearly, the phenomenon is clearly anisotropic and it follows a specific axis of rotation. So we would like to compare two graphs up to rotation. We would like our metric to be invariant under rotation. The problem is that while the Gromov-Wasserstein part is invariant under rotation, the spatial part is not. So we found as a solution a pre-alignment of all our graphs. So the idea is that you start with two spatial graphs and you can you find the maximal axis of variation of each graph and you rotate your graph along that axis. So the graph, instead of being compared in their initial position, they are compared after the rotation with respect to their principal axis of variation. So that's a pre-alignment step. In terms of the metric, the idea is to have exactly the same metric, but my coordinates A and B, so my spatial coordinates on the nodes, are firstly rotated with respect to OA and OB, which are two orthogonal matrices that represents the principal axis of variation of my set of spatial nodes. So if you have your original data set, you now pre-align your data by orienting all your graphs with respect to the principal axis, and then you compare the distance between these objects. So spatial graph, this graph of spatial graphs equipped with a fused Gromov-Wasserstein metric on the pre-aligned graph is the metric space, and it is also an orbifold because the fused Gromov-Wasserstein metric induce, of course, the concept of equivalence classes. So there are graphs that are at distance 0, even if they have not different structure, non-different position of the nodes, but they might, it is invariant under scaling, for example, because we're considering percentage of edges, of area under the edge. So we have this metric space. What we would like to do is define methods based on the metric, which is the only tool that we have here. So we start by doing testing, performing testing, because we are interested in comparing the distribution of graphs within different subjects. So what we would like to do is to perform a statistical testing where we compare the distribution of graphs, where I have the first set of graphs that follow a certain distribution and the second set of graphs that follow another distribution. And we want to test if these distributions are the same or are different, a simple testing, a standard testing procedure. In our case, the comparison is, for example, between subjects, so between patients, and between slices, because we have also these slices components. There are many ways we can do testing. One way is to use a test statistics based on entropy, basically, which is defined here. This is, again, a well-known method for comparing objects based on the metric, the dissimilarity matrix that we have computed. The results are quite interesting because we can see that we are able to compare all our patients. So here, these are p-value matrices. We can compare the patients, and we see that there are patients that are different and patients that are similar, and these reflect the different mutation in the different patients. And even more interestingly, if we look closer at two patients, for example, P2 and P3, so we look at P2 and P3, that has a very low p-value. So the distribution of the spatial graph in these two patients, we can say that is, we can reject the null hypothesis. Then we can do the test across our slices, and they are actually, we rejected the null hypothesis on almost all the slices. So here I'm considering for these two patients all my slices. So for P2, we have this first set of slices, and for P3, we have this other set of slices. Similarly, if we look at P2 and P8, that again has a very low p-value, they are also different across all the slices, while except from one. While if we look at P3 and P8, which have high p-value, they also have high p-value across all the slices. So this was a very interesting result for our collaborators, because you can see that if the distribution of the spatial graph within the heart is different across all the slices. So it's different despite the height of the ventricle. So this was an interesting result. So let's wrap up. So we have, in the second part of the talk, described how you can work with spatial graphs. So our data objects are these spatial graphs that can be obtained by using skeletonization procedure. We define a geometrical embedding for these spatial graphs based on the fused Gromov-Wasserstein distance that we have modified in order to take into account specific group actions that are of interest for this data object. And then we described how you can do testing, which is just the first step of different methodology that can be defined for this type of graphs. You can find more information on this paper by Tito Envaillé, and we are working on finalizing this paper on this specific application for cardiac fibrotic tissue. So let's conclude. What I wanted to discuss today is how you can handle unlabelled graphs, which are graphs that require a concept of matching or alignment between your graphs. So you have uncertainty around node labels that have different meanings. So you need to be able to handle this uncertainty in different ways that make sense according to the different context. And I work on two different types of graphs up to now. One is what we call the abstract graph, and the other is what we call spatial graphs. So what I want to describe is how you can handle this alignment or this how you can handle uncertainty with a specific type of alignment when you work with different types of graphs. And I want to conclude by adding just a little more about these spatial graphs. So I believe these spatial graphs are very interesting objects because they need we need to define proper tools, geometrical and statistical tools for the analysis of these spatial graphs. And these spatial graphs arise in many different applications. For example, here you have the vascular, neural, and tubular structure that you can extract from pancreas. So in the human body or in the animal body, you have a lot of these type of structures. And the standard shape analysis tool doesn't really work very well for these objects. So we are approaching this data type using different approaches. You can work using seeing these objects as realization of random fields. You can define tools for spatial graphs like the one I introduced today, or you can use tools from topological data analysis. So there are many different ways you can work with this data object, but I think there is plenty of room for developing new tools. So this is all for today, and thank you for having me. I don't know what time is it because I cannot see the time, but thank you very much. Yeah.
Thank you a lot, Anna. Thanks. Virtual clap, actually.
I'm on time. Very good.
Thanks. Any question? Just maybe just feel free to unmute yourself. Ed, please.
Hi, Anna.
Ciao, Ed. Hi, nice to see you. How are you?
Yeah, Andy, you okay?
All good.
Good, thanks for the talk. Sorry, I joined a little bit late, so apologies if I missed this particular point, but it's to do with the second half of your talk where you're first of all extracting these spatial graphs out of an image.
Yeah.
And I guess the question is how do you go about extracting the spatial graph itself out of what looks like a binary pixelated image?
Yeah.
And because from the eye I could look at one of those and come up with a slightly different spatial graph. And I guess therefore is there uncertainty in the spatial graph which comes out of that image, and is that built into the following inference engine, essentially, this uncertainty what the actual spatial graph is, because you're having to extract it from a image where there could be other kind of spatial graphs you could quite easily kind of extract from the same thing. Yeah,
that's a very good point. So the literature about skeletonization procedures is huge. So we are taking tools from the literature, let's say, but you're right. So one idea could be to build a metric that is also parameterized with respect to, for example, the number of nodes you are selecting on a specific edge, like how much I'm cutting my structure along a specific edge, as well as you can also parameterize your edge as a function. You can parameterize the underlying shape as a function on the edge. So these are other type of, these are extension of what we are doing. Let's say that we are taking the very, very, very first step using this very simplified graph. There are some papers that actually study proper function on the edge, spatial function in R2 or R3. But for this specific application, as you have such, I don't know how to say, like these edges are often very, very short and you have a lot of holes. So we thought that using just this linearization with these edges was enough. But if you study structure, for example, like this one you see here, then maybe using a proper function in R2 or R3 could be a better choice. But yes, your point is a fair point. I don't know if I answered your question, but I think that's what you asked.
Thank you.
Thanks. Anna, we have a question in the chat by Matthew Spencer. I will read it. If you have a function associated with each edge and then compute a functional distance between matching edges in different graphs and sum it over all edges, is that an example of an attribute map that leads to exactly your quotient pseudometric if you minimize over injective mappings between vertices in the pairs of graphs? Thanks.
Okay, wait, let me read it again. If you have a function associated with an edge and then compute a functional distance between matching edges in different graphs and sum it over all edges, is that an example of an attributed map that leads exactly to your quotient pseudometric? I don't know if I understood the question. Can you maybe add more, Matthew, or ask me directly? It'd be easier to understand what do you mean. Because I don't know if you are referring on the way I am on the object I'm extracting, like related to the question, or more on the metric I'm using?
Maybe. Matthew,
okay, thank you.
Okay, please. I will try to mute you. Let's see how.
So one thing that confuses people from time to time is the fact that I define my spatial graph as a metric space. So I have this metric, this geodesic metric, what is called shortest path distance on my graph. And my graph object is actually a metric space. So I don't know if this is what you mean. Like maybe the question is related about the fact that I'm using this Gromov-Wasserstein type of distance between these metric spaces, which are my graph. But I don't know if this is what you actually mean. I don't know if there are other questions in the meantime.
Correctly. So is there equivalence between computing functional distance like summing over all edges and the quotient pseudometric that I think you had on one slide? So is there equivalence between the two? Please understand.
Is it so?
Are they the same?
Is he referring to this metric or the one between abstract graph?
Something related to the quotient space.
Yeah, this is also a quotient space somehow, but the group action is complicated. So it's referring to my quotient metric, this one here, right? Sorry, just thinking. Okay, so for this type of adjacent metric, you have a distance that is based on distance function on the element of the adjacency matrix. Yes, so you mean instead of having like normal, so now I'm using as a distance between adjacency matrix just the Frobenius norm. And what you're saying is, what if you're using a distance that is based on distance functions on elements of your adjacency matrix? Yeah, you can change the distance between adjacency matrix with something else. This induces a quotient metric only if this distance is element-wise. So as soon as you have an element-wise metric, like the Frobenius norm, where I'm comparing edge to edge, then you induce also a metric between equivalence classes, so you can change the metric. So I don't know if this is what you were interested in, but yes, great. Yeah, you can define other metric on the between adjacency matrix. Thank you for your question, Matthew. We made it. I hope I answered.
Thanks. Anyone else? Just please unmute or write in the chat. Shortly, two questions I would have briefly. Firstly, is this related? I mean, you have the Gromov-Wasserstein distance and similar distances, and metric spaces and distances are connected, I think, also to different topologies connected to probabilistic objects and similar things which are related to random graphs. You have question is, could you do this in other topologies like weak topologies? But probably this would depend on type of the network. And secondly, more foundationally, if you talk about geometric statistics, is there a necessary connection to networks and to graphs? One would assume that geometry as such could also, even if it would be metric geometry, could this be extended to other types of, not just topological, but say, I don't know, other types of data analysis?
To start with your first question, I think you are referring to the fact that I'm using some sort of distribution of mass over the nodes, right? Are you referring, because so there are different things. So one thing is the fact that these metrics are based on basically defining this coupling. So they require a mass mu and nu, which are measured associated to each node. So this can be changed and modified according to what you are interested in matching. So you can also change the balance of the mass of the measure on different nodes. So this can be done. Another thing is studying the proper distribution on this metric space, which is what we are trying to do with the testing procedure. So this is another point. So we haven't studied extensively how you can characterize the distribution of spatial graph in this metric space. So I don't know if your first question was related to this point. Yeah. So this second part is still at the very beginning. So this metric doesn't have a lot of properties. So for example, it's not of strong negative type. So there is not much you can do to understand to define a proper distribution on this metric space. So I think we're able to define a distance, but there is not a lot of properties that we understand. So this is first question. The second one, can you repeat the second one?
So the question is, if you talk about geometric statistics, could this geometry part be related also to something else than networks, graphs, and even something different than metric geometry? Thanks. This is more.
Yeah. So okay. So the analysis of so how to extend statistical tools to metric spaces and to quotient spaces that are non-manifold is much more general than graphs. So there are plenty of other data objects that are described in metric spaces which are non-manifold. A simple example are trees. So when you have a population of trees, for example, phylogenetic trees, then you are in an usually you end up in an embedding that is not a manifold and doesn't have any sort of tangent space, well-defined tangent space. So any tools that are defined for these type of spaces can be applied to many other contexts, and is actually an interesting line of research because it's a relaxation of the standard manifold statistical tools for manifolds. And regarding the spatial graph, I think calling them spatial graph, I don't know if it's a good strategic choice, but this theory can work when you have shape that has a very complex structure. So you cannot really work with landmarks or with standard shape analysis. So on a more specific note on spatial graphs, I think they can be applied for describing textures or in general shapes that has a high number of holes. So this can also be extended for other data objects that doesn't really look like proper graph in our, that we don't refer directly as graphs, let's say. So I don't know if I answer, but.
Okay. Thanks. Thanks.
You're welcome, Andrea.
Anything further? The audience? There is one additional, I think, coming. Maybe when he types or she, how strong is this connected to topological data analysis?
They're very connected. So we are looking at spatial graphs. I mean, abstract graph, not that much, but we are using some tools from TDA for studying spatial graphs because building what they're, for example, persistent diagrams out of this spatial graph is a very smart way to summarize the information that we have on these graphs. So yeah, let's say TDA is a very interesting and powerful tool to work with spatial graphs, and we are looking at this literature as well.
Thanks. Thank you.
Okay.
Okay. Is there anything else by anyone? Otherwise, thank you a lot. I think it was very, very interesting, and we could probably also.
Thank you very much for having me, Andrea.
Thank you. Thanks. Okay.
Thank you for having me.
So, thanks a lot. Stay in touch.
Thank you so much. Thank you, everyone.